Okay, the penultimate honors physics homework assignment, momentum and impulse, homework number 28. Here's question number 1. On the left-hand side, it gives me a little bit of background on impulse and momentum, which was the subject of the lecture, so I already know all about that, but reread it if you like. So it has parts A, B, and C, and in this situation is a classic of this type of problem. Baseball game, batter swings to get a good solid hit. He swings and applies a force of 12,000 newtons to the ball for 0.7 times 10 to the minus 3 seconds. Assuming that this force is constant, what is the magnitude J of the impulse on the ball? Well, if you listen to the lecture, you know I don't like to use J for the impulse, but a lot of folks do. J is just delta P, the change in momentum. And my impulse momentum law tells me that delta P is equal to sigma F delta T. So in this case, there's only one force acting on the ball. It's the force that the bat exerts on the ball. And delta T is the time. Both of those are given. So for part A, all I need to do is take my 12,000 newtons and multiply by my 0.7 times 10 to the minus 3 seconds to get the impulse delivered to the ball. So we often visualize impulse by drawing a graph of force as a function of time. So this graph appears over here. I have the force that the bat exerts on the ball as a function of the time over which that force acts. If we assume that the force is a constant, then this graph is a rectangle. So the magnitude of the net force versus time for graphs, often in physics, geometrics, blah, 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 blah. For this graph, the area of the rectangle corresponds to the impulse. And that's a thing that we learned about in lecture. If both the graph representing the constant net force and the graph representing the variable net force, so the force doesn't really look like this. They give me a second graph here. Do you see it's one of two? If I click on that, I see a more realistic graph. When the baseball and the bat come into contact, the force of the bat starts out small and then rapidly grows to a maximum value. You can imagine watching this in slow motion as the ball compresses. And then the force diminishes again to zero quite rapidly. So this is the realistic graph. This is the idealistic graph. If they're both supposed to describe the motion appropriately, then the thing that they must have in common is the area, because the change in momentum of the baseball is a fact. The impulse is a fact, and so those areas have to be the same. And there they are, graphed one on top of each other, so that's looking good. Assume the pitcher throws a baseball so that it travels in a straight line parallel to the ground. The batter hits the ball so it goes directly back to the pitcher along the straight line. That's telling me that my conservation of momentum homework is due tomorrow. The impulse of the ball caused by the bat will be in the... Okay, so I'm assuming that the pitch is in the positive direction. And so the pitched baseball has positive momentum. When the bat exerts on a force on the ball, then, the bat is going to be exerting a force in the negative direction back toward the pitcher. Since the change in momentum is in the direction of the net force, I can tell that by my law right here. The change in momentum is equal to the force times delta T. Since the change in momentum is in the direction of the force, then the change in momentum is in the negative direction, which means the impulse is in the negative direction. Part E, it just goes on and on and on. Now assume that the pitcher throws a baseball parallel to the ground with this speed in this direction. The batter then hits the ball so it goes back to the pitcher. What is the ball's x component of velocity after leaving the bat if the bat applies an impulse of negative 8.4 Newton seconds? Do I have an equation for this? Apparently I did not prefab an equation for this, but it's easy enough. The impulse that I'm given, negative 8.4, is delta P. So I want to set that equal to the final momentum minus the initial momentum and simply solve for the final velocity. When I do, that final velocity will be negative. That's no surprise at all because the baseball is hit back toward the pitcher in the negative direction. Yeah, go to the next item now. Fine. Super. Number 2. What speed do a bicycle and its rider with a combined mass of 100 kilograms have? At what speed do they have the same momentum as a 1,500 kilogram car traveling at 1.2 meters per second? Well, they just want to have the same momentum. So I'll take the mass of the car multiplied by the car's velocity, and that's a certain quantity of momentum. And I'll set that equal to the momentum of the bike, m times v. I have the mass of the bike and the rider together, 100 kilograms, and I want to find the speed of the bike. So 1,500 times 1.2 divided by 100 kilograms is going to give me v, the speed of the rider. This question was really just knowing how to calculate momentum. Not really tricky at all. This tennis ball is served at 45 meters per second. Starting from rest, what impulse was applied to the ball by the racket? Well, the impulse is the change in momentum. So all I have to do, realizing that the tennis ball had zero initial momentum, its change in momentum is equal to its final momentum, which is its mass times its velocity. Have a care. The mass here is given in grams. You would want to convert that to kilograms. 0.057 kilograms times 45 meters per second is the impulse delivered to the tennis ball by the racket. So a student throws a 130-gram snowball at 85 meters per second. That'd be quite a throw. 8.5 meters per second at the side of a schoolhouse where it hits and sticks. What is the magnitude of the average force on the wall if the duration of the collision is 0.17 seconds? Well, I'm going to use my impulse law again. First of all, this snowball has momentum and then it doesn't. The snowball's initial momentum is its mass times its velocity. Again, the mass is given in grams. So 0.13 kilograms times 8.5 meters per second will be the momentum of the snowball. The snowball then loses that momentum. So the impulse is the negative change in that momentum, is equal to the force exerted by the wall multiplied by time. Well, they give me the time is 0.17 seconds. So simply divide the momentum of the snowball by the time, 0.17 seconds, and you get the force in newtons. Problem number 5, another graph problem. What's the impulse on a 3-kilogram particle that experiences the force described by the graph? It's weird that it says 3-kilogram particle because I'm pretty sure I don't care. What I need to do is find the area under this graph, because the area under the graph represents the impulse. You should be very careful. This is milliseconds on the time axis. I think a lot of folks will trip up and get it wrong because this graph is in milliseconds, is 10 to the minus 3 seconds. So here it's 2 milliseconds wide and 1,500 newtons high. You simply multiply and you get that positive impulse. In this part of the graph over here, you see the forces become negative, and so the impulse is negative. Area calculated below the time axis is negative area, negative impulse. Well, here it's 3 milliseconds is the duration of the pulse, and negative 1,000 is the force. So calculate the positive impulse, subtract the negative impulse, and then you get the total impulse in Newton seconds. Notice, or kilogram meters per second, if you like. Notice I didn't need that 3 kilograms at all. So here I have a 0.72 kilogram air track glider that collides with a spring, one end of the track. Here's a graph of the velocity as a function of time. You see what happens? It has a velocity of -3, and then it has a velocity of +3. So what's happened here is the spring glider is traveling in the negative direction. It hits the spring slows it to a stop, and then the spring accelerates it off in the positive direction again, where it ends up with the same final velocity. This doesn't surprise me at all because springs conserve energy. So this glider has a certain kinetic energy to start with, and it'll have the same kinetic energy to finish with, which is why the velocity doesn't change, because the kinetic energy has, well, I say the velocity has changed because it's changed direction, but the speed hasn't changed because the kinetic energy remains the same. Anyway, how long is the glider in contact with the spring? You look at this graph and you say, well, I can't tell. Do you see? Because here is where the velocity starts to change, and here's where the velocity stops changing, but there are no tick marks on the time axis. Well, look, there's another graph. If I click, I get a graph of the force as a function of time. Again, there's no tick marks on the time axis, so I can't, here's where the force started and here's where the force finished, but I can't do that. But I can use my impulse momentum law, because I know that the area under this graph is equal to the change in this momentum. So the first thing that I want to do is calculate the change in momentum, calculate the impulse. Well, the final velocity is 3, and the mass is 0.72. So the final momentum is 3 times 0.72. The initial momentum is negative 3 times negative 3 times 0.72. Or 0.72 times negative 3. That's the way you want to go. So I can calculate the change in momentum by the final momentum minus the initial momentum, but the initial momentum is negative. So I end up adding those momenta together in my algebra. And now I've computed the impulse, the delta P. That impulse is equal to the area under this graph. The area under this graph is the area of a triangle, which is 1/2 the base of the triangle, so 1/2 delta T, multiplied by the force, which is 36. Well, I already know the impulse, and so all I have to do is take the impulse and multiply by 2 and divide by F. I know it's become a little bit confusing. I've written it out as equations here. I can calculate the change in momentum here on the left-hand side of the equation. It's simply the mass multiplied by that change in velocity. The change in velocity is 3 minus negative 3, which ends up being 3 plus 3, which is 6. 6 times the mass. So I know this whole left-hand side. The right-hand side is the area under the triangle, which is 1/2 the base of the triangle multiplied by the height of the triangle. This is 1/2. This is 36. Doing a little algebra, multiplying 2 over to this side, dividing by F. I can use this expression to calculate delta T, the time that the glider is in contact with the air track. No, I don't want to. Stop, go away. All right. Final question. This question was really tricky, and I considered removing it from the assignment. But my students are smarter than I am, because a whole bunch of people got it right off the bat. Huh, that's strange. Anyway, here I have a graph of force as a function of time for a woman who is jumping. Notice here that the force is constant for a little bit, all the way up until 0.2 seconds. What's going on there is she is standing. She's just standing there. So the upward force that the ground exerts on her is equal to her weight. This information, the first part of the graph here, is what makes it possible for me to work out the mass of the woman, which turns out to be 61.2 kilograms. You just take 600 newtons and divide by 9.8. So I know the mass of the woman. She doesn't start jumping until 0.2. And she doesn't actually leave the floor until 0.5. I can tell that she leaves the floor at this point, because this graph is not a graph of the net force. It's a graph of the force that the floor exerts on her. And right there at 0.5 is where the force that the floor exerts on her becomes negative. Now, working out the impulse here is quite tricky, because there's more than one force acting. There's the force of the floor, and then there's the negative force of the force of the floor pointing upward on her, and the negative force of gravity pulling downward on her. So what I chose to do was to change the graph, so the graph would make it easier for me to calculate this thing. What I did was it's the same graph, I just cut it to pieces. I took the graph and I shifted it down, so it became a graph of the net force. I shifted it down by 600 newtons. So I essentially subtracted the weight from the graph of the force exerted by the floor. And now I have a graph of the net force as a function of time. Now here's a tricky problem that occurs once I do that. The point at which the force graph crosses the time axis is no longer 0.5 seconds. I have to calculate actually what it is. And so I did a little rough estimation, and I'm saying that it's about 0.475 seconds. So now, to calculate the impulse, I have to calculate the area under this big triangle and the area under this little triangle and add them together. The big triangle area will be positive. The small triangle area will be negative. So here I am calculating those areas of triangles. Of course, area is 1/2 the height of a triangle times the base. And so 1/2 of 1,800 newtons, because I slid it down by 600 newtons. 1/2 times 1,800 newtons for 0.275 seconds. That's, see, this would be 1, 2, 3 would be 0.3 seconds, but I've subtracted away you get it. 0.025 seconds. I subtracted away. So 0.275 seconds, and I get the positive impulse, 247.5 Newton seconds of impulse. The small triangle, which is negative impulse, is this tiny little wedge of a triangle secreted in here, is 1/2 of 600 newtons times the remainder of the time, 0.025 seconds. This is negative impulse. The total impulse then is this impulse minus this impulse. Well, look, it's 7.5 and 7.5. So my total impulse is 240 Newton seconds. So then, to calculate the change in her velocity from 0 to whatever it is, I simply take that impulse, 240 Newton seconds, and divide by her mass. And I get 3.9 meters per second. This was a significantly challenging problem. So you shouldn't beat yourself up too much if you found it difficult or impossible to do. It took me a bit of messing around to figure out exactly how I was going to do it. And ultimately, I ended up making a new graph and things like that. So I put a significant amount of effort into that problem. But there it is, number 7 on the penultimate homework assignment. Homework 28. Momentum. And